Hey everyone, and in today's lesson we're learning about modular arithmetic. This is one of my favorite parts of discrete math, so let's get right into it. Now before we get into actually learning about modulo, I just want to give you guys a quick reminder of what we say is divisible, not divisible. Just remember stuff like A divides B and stuff like A does not divide B. Also, let's remember the division algorithm, which is A is equal to NQ plus R, where Q is the quotient and R is the remainder. Now, I'm not going into too much depth here, but I have a whole video about it, so if you want to watch that, I will link it in the description, but I just wanted to remind you guys that this is the division algorithm, and it's super important to know how it works. So if you don't know how it works, maybe watch that video first, then come back to this video, because a lot of what modulos are depends on this. So now what is a modulo? So in simple terms, a modulo, or sometimes for short we say mod, is the remainder, or you could see here it is the remainder of a division. So essentially it is just the leftover part of that division. So what does that actually mean? All that's saying essentially is A, and we'll say mod n here, okay, is equal, right? It's actually just equal to the remainder of the division, but the division of what? Well, all it is the division of A by m. So essentially we're going to divide A by m, and the remainder that we get is the modulo. So now let's look at a few examples, and this will be quite concrete. So let's just, for instance, say 5 mod 3. Okay, so what is this saying? And all it's saying is take 5 divided by 3 and then give us the remainder, and that is the answer to this modulo. So quickly, there's a couple ways to figure this out. We can use the division algorithm, which says 5 is equal to 3 times a quotient. Well, in this case, it's just going to be 1 plus a remainder of 2, right? By using the division algorithm. Again, I have a video that goes over that more in depth, but essentially then this gives us that the remainder here is 2. Okay? Or another easy way, as I like a trick, is just do long division, right? So take these numbers, take your A and your N, and you can just say, well, okay, so 3, and use long division, and 5. And then you can do the same thing here, and the last thing here is your remainder. Now let's do one more quick, harder example. So let's say 33 modulo 12, right? Again, the numbers got bigger, but it's still the same thing. It's just saying divide this right here by this right here. So what I can do, the simplest way that I like to do it, is just say, okay, well, 12 goes into 33, and I'm just using my long division from, middle school here. So, well, 12 goes into 33. Well, let's think about that. It only goes into it twice. What is 12 times 2, right? So I'm just using my long division, and then I do my subtraction in this case, which is 9. So the remainder is 9. So this evaluates to 9. And now something that I hope you're connecting with your previous discrete math lessons is the fact that modulos can basically be seen as an equivalence class, right? So let's, for instance, take mod 4, right? So actually we'll just say A mod 4, right? So what essentially we're saying is that A, regardless of what it is, it's going to be equivalent to one of these values here, which lies in the set of 0, and I'll explain this in a little bit too, 3. Now you might be like, what are you talking about? But let's quickly think. When you talk in mod 4, all we're saying is the possible remainders is either 0, either 1, either 2, or 3. And it can't be, well, 4, because 4 is just the same as 0, because you can, this divides by 4, right? So there's no remainder 4, it's just the same as 0. So we can see that there's only 4 possible values that we can have for a remainder. Now, what's interesting about this then, that must mean that there are multiple A values that have the same output. So then that means something like 3 mod 4, right, which is just equal to 3, right, because what is the remainder of 3 divided by 4? It's just 3, right? But let's think, what else divided by 4 has a remainder of 3? Well, 7 mod 4 has a remainder of 3, right? Again, if you don't know why, you could just put it in the long division. It fits into it once. You plug it in, the remainder gives you 3. Which then nicely brings us into this idea of congruence. And I want to use this with something with wheel math first, which is a visual way of seeing it, and then we'll get into the formal definitions. Now, while my wheel is not too great due to my art skills, I hope it gets the point across. We can think of modulo 4 in terms of a wheel with 4 major sections, right? And the major sections, as you could see, maybe here's the first one, so that's major section 1, and then major section 2, and so on. So we have these major sections and so on. So now I'm just going to start counting from this box here. So I'm just going to say 0 goes here, 1, 2, 3, and now I'm going to go to the next, wheel, essentially. You can think of each of these as a wheel. I'm going to go to the next wheel. I'm going to say this is 4. I'm going to stay 5, 6, 7, and again I go up 8, 9, 10, and 11. So something super interesting about this now is this is going to tell us a little bit about congruence in a little bit of a visual way. Now we have 4 major sections, so we can say this is the same thing as modulo 4, right? I already mentioned this. And what's interesting about this is it basically tells us that from the inner circle right here, so from the inner circle there, it tells us that any number that is within that major section, so for instance, for 0 in this major section, right? It's telling us the remainder of that number in that section when divided by 4. Right, which is our mod. So you can see that means then it must be the case that 8, right, 8 divided by 4 gives us a remainder of 0, and that is true. And then it also says then that all the numbers in this section, where the 1 is, when divided by 4 give us a remainder 1, which is, again, we know that to be true because, for instance, 9 divided by 4 is gives us a remainder 1 because it's 8 plus 1. And the same thing goes for here and so on, right? So each section, you can see, it tells us the remainder. Right? And this is a wheel for mod 4, but I'm sure you can imagine that the number of sections it has just correlates and corresponds to the mod that it is, okay? And something more interesting as well, it actually tells us in steps that if you go from 8 to 0, for instance, what it tells you is that if you take one step and then take another step, basically it tells you how many steps you need to take. So in this case we took 2 steps, so it basically is also telling you the quotient. Now why is this important? Because, well, you can actually count in this way, and you can add, because if you think about it, well, I can just add from 0. Let's say I want to add 3. All it's doing is going 1, 2, 3, right? So if I add 3 to 0, I'll end up in this section because I just added. So I went forward 1 step, 2 step, 3 step, right? Right? So we can add in this. And so then we can also subtract, because if we start at 3 and I want to go down 2, I can say, well, that's 1, 2, and I'm back at 1. So the reason I bring this up is because something super interesting happens when we look just within one section. So for now, let's just have our focus on this section right here with the 3, remainder 3, right? So what we say, notice this. If I subtract a number from this section by another number from this section, notice something that happens. So I'm just going to go backwards here, okay? So just follow me. I'll use a red so it's easy to see. So remember, if I went forwards this way, all I have to do is go backwards this way, right? So if I went forwards in counterclockwise to go backwards, or wait a minute, I mean clockwise to go backwards, I need to go counterclockwise, sorry. So if I want that, so just to make sure, if I want to take 7 away from 11, I just have to go back 7 steps from 11. So I'm going to go back 1, and then I'm going to go back 2, and then 3, right? And notice that here I need to go to the next wheel. So I went back 3, now I'm at 4, 5, 6, 7. Interesting. So I ended up in the green section, and the reason I highlighted green is because that means we have no remainder, right? So I subtracted from the same section and I ended up with green. Okay, does this also work? Let's take I'll take this pink here. So let's see if it works again with 6 and 2. So if I want to take 6, I want to go subtract 2, I just have to go backwards 2. So I go 1 back and then I go 2 back. Interesting. So we notice that if you go from within the same section, right, and you take a number and subtract it, then you always end up in this green section, right? So interesting. Let's just keep that in mind. So now with that wheel math in the back of your head, let's come to this formal definition of a congruence, which just says if A and B are in the set of the integers and M is in the set of the positive integers, and I missed an N here, so then, right, then A is this weird 3 lines to B. So this 3 weird lines, we call it congruent. So this is congruent. So then we say that A is congruent to B. Mod M, if and only if M divides A minus B. Now, I'm not going to go too into depth about what the proof of this is, but let's quickly see it in action. So I have moved the definition to the side and made it a little bit smaller, and I have now 2 points that we want to, 2 examples that we want to determine if they are congruent from this definition in the top right. So let's quickly work, and I'll work in blue here. So 2, is it congruent to 6 in mod 4? Well, our definition says that M, which is the modulo here, 4 must divide the difference of A minus B. So let's quickly see. A is, in this case, 2. 2 minus 6 which is just -4. And the question is then, does 4 divide -4? Well, yes, it does. Therefore, this one is congruent. So we could say that 2 is congruent. Now, to 6 in mod 4. Note that I'm not saying that 2 is divisible by 6 or that 6 is divisible by none of that. I'm just saying that their remainders are the same. Now, let's move on to the next example. So I'm going to do my work up here a little bit. So again, same thing. All it means is we want to see if this divides the difference of these two. So 24 minus 14. Well, this is going to give us 10. And does 6 divide 10? Well, no, it does not. So in this case, it is not congruent. Okay, so now I want to point out that this beautiful formal definition that we just learned about is really just saying the same thing as the fact that their remainders are equal. So I just want to make sure this hits home for a lot of you. We're basically saying that A, when it's congruent to B, and we'll say mod n, right? So in mod n, when we're saying this, all we're saying is that, well, A, if you take A mod n, and if you take B mod n, then their remainders are the same, right? As in you'll get the same evaluation. So we could say something like A mod n, right, is equal to B mod n, right? So we're saying that when you evaluate these two, we're saying that this gives you the same value as this, right? Essentially saying that when A is divided by n, it'll give you the same remainder as B divided by n. So now I'm going to bring back the idea of the equivalence class. So let's talk in mod 4, right? So in mod 4, remember that we can have an equivalence class, and the reason we can have an equivalence class is because there's different values, right, that in mod 4 will give us the same output 0, as in they'll have the same remainder 0. Like really quick, right before we start, I just want to remember that in mod 4, the only possible remainders are 0, 1, 2, and 3, right? Because, well, 4 and anything more can just be represented as one of these. So 4 can be 0, 5 can be 1. So it doesn't make sense to have more. So these are the only remainders possible. And note that it's always 1 less than the mod itself, which is the last possible remainder, right? So anyways, so all of the, values in mod 4 that are equivalent to 0, we can basically say, well, let's quickly just say -8, 4, 0, 4, and 8, and so on. And bear with me, I'll show you how to get these numbers, like how I came up with these numbers in just a second. But basically what we're saying is that all of these numbers here are congruent to each other. That is, -8 is congruent to -4. We can also say -4 is congruent to 8, right? But we're talking all in mod 4, so you can always imagine there's a mod 4 here, just because that's super important. Let's see if that fits. Okay, it doesn't fit. Don't worry about it. Okay. So what we're basically saying is that all of these are congruent to each other because they're all the same. So essentially, this is congruent to this. It's congruent to this. This is congruent to this, and you can see they're all congruent to each other. So that's what I was trying to say earlier, and I hope that you can see the link between equivalence classes, the potential remainders, and sometimes we call these residues as well, and how they can be related to being congruent. Now, for the next step, we don't have to just stop there. We can say, well, what are the equivalence classes for 1? And if you just wanted to know where to start or how to evaluate what's in the set, well, remember that whatever number it is that you start at, so in this case 1, right, in any mod, that number, if it's less than the mod itself, right, it will just always give you that remainder. So you can always start with that number as the first thing. So you can always say 1 in any mod, as long as it's not 1 itself, right? As long as it's less than the mod, so in this case it is less than 4, it will give you 1 again, right? Because, well, if you just do I'll just show you, if you put 4 into 1, well, it doesn't fit into it any times, and then 0 minus whatever that is will give you that remainder. So the same thing applies to 2, the same thing applies to 3, right? So long as this number is less than the number that you're dividing. So 1. Now you might say, well, what is the next number? So now let's quickly recall that wheel example. Essentially, all we're saying here is we want values that are in the same section that 1 is in. Now remember that we go up, depending on the mod, we have to go up a full mod. So in this case, in mod 4, right, we have to go up 4 sections. And I'll go back here, actually. If you want to know what number is in the same section as 1, all we have to do is just add the number of sections and we'll end up in the same section. Essentially, we're doing 1 full loop around. So I know this is getting a little bit messy, but hopefully you can follow along with this arrow. I'm going 1 full loop around, and I'm going to end up in the next wheel in the same section. Okay? So essentially, we can just add 4. So let's see, 1 plus 4 is 5, and I can say 5 plus 4 is 9, and then I can keep going, adding 4, and this will give me the equivalence class of 1, and I can do this with 2. Again, I can start at 2, and I can add 4, so that will give me 6, and plus 4 will give me 10, and so on, right? So essentially, what you should notice here now is the fact that basically you can count up and down. By the way, you can also go down. Just because I didn't go down does not mean you can't go down, right? You can go down, but essentially you can go up or down in your mod, and you will get the equivalence class for this. And hopefully that visual wheel that we talked about earlier helps you see that as well. Now, what do we take away from this? All that we can take away from this is basically saying that any number that lies within this set, right? So, for instance, 1, 5, 9, 13, they're all congruent to each other. So we can literally say 1 is congruent to 5, which is congruent to 9, which is congruent to 13. And the pattern, if you noticed it, we can basically just say it's 1 plus 4x, which is just saying that you add a multiple of 4, right? And you can keep going on and on and on. And the same thing can go on here, right? So you can say 2 is congruent to 6, to 10, and we can say by extension 2 plus a multiple of 4. So hopefully that all makes sense. And so these are all congruent, obviously in mod 4, so let's just specify if you weren't sure. So we put it in the brackets at the end to just make sure that we know in which mod we're talking about. All right, that is all for today's lesson, and next up we're going to actually learn how to use this notation to do real arithmetic, like add, like subtract, and multiply, and we'll talk about divide a little bit more in detail in the next lesson, and also how to solve congruences, right? Similar to how we solve equations. So thank you so much for watching.